I'm Sébastien. I'm a PhD student in Geneva University, so I work with Georges Menet and Sylvia Ekstrom, and today I'm going to talk about rotating pulsational pair instability progenitors at both very low and slow metallicities. All right, so let's first talk about the final fate of stars. So of course we know that supernova, that massive stars finish into a supernova explosion, leaving usually either a neutron star or a black hole as a remnant. But there's a mass range, what we could call the black hole gap, where we do not expect to see any remnant. This is due to pair instability. So it's when inside your star, you have enough energy for a photon to transform into a pair of positron and electron by interacting with the quantum field of an atom. And so this will reduce the total rotative pressure you have. And so if the pressure does not scale fast enough compared to the density, that's what this gamma 1 means, when it's under 4/3, you cannot satisfy anymore the hydrostatic equilibrium, and then you become dynamically unstable. And this collapse can lead to usually oxygen burning, but at an explosive rates. And the explosion that will happen will lead directly to complete disruption of the whole star, and so the whole mass will be converted into a supernovae. So this was already theorized in the 60s, but it came back 15 years ago with the first observation of superluminous supernovae. But the main problem was that core collapse supernovae model were not able to produce such energetic events. That's where the idea of pulsational pair instability supernovae came. It's kind of a pair instability that failed. Only a part of the star will be ejected with very high velocity, so it's a huge chunk of a star still. It can be from a few solar masses up to tens of solar masses, and ejected at very high velocity. So of course, it's there's a lot of energy inside. This was challenged a bit, this idea of pair instability with the newly observed medium mass black hole. They were kind of populating this zone when we did not expect any black hole to be there. To be more precise, there are really just above the lower boundary that we were expecting. So it's also challenging if we are maybe wrong, kind of, if we do not grasp the boundary correctly with the stellar evolution model, or if the pair instability happens at all. So there's other challenges also, because superluminous supernovae happens at solar and then higher metallicities, and the problem is that for these very massive stars, you will have a huge mass loss that will result to a star with a really small core, kind of small, that will prevent the star to go into high temperature and create this pair creation, and so pair instability. One idea was that part of O-type stars have a strong surface magnetic field, and so it could kind of quench the mass loss from the star, and so you would kind of keep a part of the mass loss, and this would allow the star to go to much higher temperature inside the core. So this combined to the rarity of VMS at near solar metallicity could possibly explain why we see not much, but a few superluminous events at high metallicity. So this was explored by Georgi and collaborators in 2017, where they tried to model with the Geneva Stellar Evolution code, rotating models with modest surface magnetic fields. So here you can see, for example, the dashed line is a rotating model for 200 solar mass without surface magnetic field, and the black one is with surface magnetic field. And so you can see you can keep a bit more mass during the evolution of the star. This will lead, in fact, if you look into this evolution diagram also of the central temperature versus density, central density, sorry. And so this the model will go, the star will go to much higher temperature for a semi-evolution stage. And so even if you look at the last models here, you will see that you cross the pair instability zone. So it could be possible to kind of tackle this problem at high metallicity with magnetism close quenching. So yeah, there's of course different pros and cons about parent instability, but you have this superluminous supernovae that kind of could be explained by pulsational parent instability. The presence of a black hole mass gap that could also give a guess. But of course, as I said, you have these high metallicity superluminous events that are really challenging to understand due to mass loss, and this lower boundary that is now not so confident with a new observation of these black holes, massive black holes. So the idea is to explore both this magnetic mass loss quenching and also the dependence of these boundaries, so the dependence of all the initial conditions and the physics input you can put into a stellar evolution model. So what first we did was to implement the pair, create a new equation of state into the Geneva stellar evolution code. So now we can take into account correctly the pair creation. So here you can see again this gamma one inside it's the structure of a star. So when it's go below 4/3, you are now unstable. So here it's two different stars, but at the same evolution stage. And you can see, for example, that a more massive core will lead to different outcomes in terms of instability. Here on the outer part of the core is unstable, while here full part of the core is unstable, and so it will lead to very different outcomes in terms of pulsation or full parent stability currently. So maybe I can show you some examples. So here is a 250 solar mass at 10⁻⁵, so very low metallicity. What's really interesting is that you can see already this non-rotating model going to the red after a troubling life, ending it as a parent instability supernovae, while the other model is going through a quasi-chemically homogeneous evolution due to rotational mixing, and so it will stay much more longer to the blue after finishing and after finish his life also into parent stability supernovae. What's interesting is when we go to the equivalent diagrams of these two stars, so the gray area here are the convective zones, the white area, the radiative zones, this color, this blue colored line here, the hydrogen shell burning, the helium shell burning, and the red here is the carbon burning. The magenta zones here shows you where in the star you have this gamma 1 below 4/3, so where locally you're becoming to be unstable. And so you can see here already the instability developing. But what's interesting here is to see that, of course, we do expect a much larger core due to rotational mixing compared to the non-rotating one. But you also have a much larger mass loss in the non-rotating model due to the fact that it spends, in fact, most of its advanced stages in the red. And so you'll have, just with rotation, very different outcomes in terms of structure, because you'll have a much larger core, for example, and a much larger envelope. So yeah, and at the onset, so you have both stars that are that have the core completely unstable and will explode. And at this point, if we look at the yields, so the abundances profile of each of these stars, you can see already that you have a much larger quantity of metals in the core, of course, because it's more extended, and a larger envelope. So both of these models in exploding will lead to very different outcomes. And so it's really interesting to probe all these different physics and initial conditions to understand more what we see and what we could see in terms of supernovae. So the idea here is to do a full grid of very, very massive stars, so really to explore the more extreme cases with a large range of metallicity to see how its impact, of course, from population-free stars up to solar models with different rotation rates. And as I said, try to investigate the magnetism mass loss quenching, mainly at solar metallicity. And so this can lead to much more mass kept here. You can see, for example, here it's the 10⁻⁵ metallicity, so very low, mass loss. Here it's the solar metallicity. So a lot of mass loss, of course, and in between magnetic mass loss quenching that help you to keep a much larger core and could lead to possible progenitors of pair instability or just pulsational pair instability, even at high metallicity. So with this whole grid, we do hope to be able to explore more of the nucleosynthesis characteristic by this pulsational pair instabilities, how we can infer a bit more about light curves and the energy produced and the amount of energy we have for each of these progenitors, the presence either or not of remnants, and how the final rotation of this progenitor can have an impact on the spin and so of magnetars, for example. And as I say, this controversy around this black hole gap, how the boundaries are independent from the different initial conditions and the inputs, but also the other way around. You can think about how this new constraints on the lower boundary can be helpful to stare astrophysics as a constraint for different, for example, nuclear rates, like VC12 alpha gamma O16, that have a great impact, of course, on the CO mass core, and so it can go also the other way around. And finally, we'll try to push all this grid of models into a 3D spherical simulation code, who's called Push, and we'll try to see how the explosion is impacted by all these different parameters. Thank you.